All right, so up until now, what we have seen is the way we try to model the information that we have and the kind of models that we can fit, especially only the Markov models. And we try to fit these Markov models and we try to basically sometimes prove that yes, the assumptions hold true, and that is why Markov model is indeed a good model that we can fit, or at least a good approximation that we can try to answer some questions using. So now onwards, what we are going to try to do is fully dive into practical purpose of studying the kind of stuff that we have yet studied. So basically, let us say if you are given some data about people's lives, so you are observing some lives. So when I'm talking about observation, maybe observation period you define as the time when a particular policyholder comes and gets the insurance policy, and up until he either retires or he either dies or something, at least until the observation ends for a particular life. So there will be some technical issues that will of course bother us, because not every time data is as clean as it should be. Not every time data is ideal to suit the theoretical models that we will propose. So we'll try to see what all adjustments we can do, and we'll basically try to see how we can try to come up with reasonable estimates of the questions that we try to answer. So in today's lecture, the question that we will try to answer is something like, let's say, the mortality rate. So I guess we have studied this two-state model previously. Just give me a minute. Yeah, so the kind of models that we studied in two-state Markov model, does anyone remember? We only had two states, right? One was alive and the other one was dead. So the only transition rate we knew about was the mortality rate. So what is the chance that the person will die in the next moment, given that he is alive today? So sometimes we'll try to figure that out. But now what we will concern ourselves with is not only the probability that the person will die in the next moment, but knowing that, what is the chance that this person will die in the next 5 years, or what is the chance that this person will survive for the next 10 years at least? And these are of course answered by TPX and TQX that we have already studied. So we'll look all of these in much more detail in today's lecture. And again, today's lecture is mostly going to be introduction to the to some terminologies, I would say. And then in forthcoming lectures, we'll again deep dive into the techniques that we'll be studying today and the relationships that we will study today. So the relationships are actually very much more important. So let us start with, so first of all, whenever we talk about decrement in terms of this particular subject, what we mean is not only death. So sometimes if, let's say you are looking at the alive death model, then the decrement would be death, because once a life dies, you do not observe them anymore. But decrement in general involves anything that would render a particular life to not be any more observable. And that can be anything. So sometimes a person could withdraw the insurance policy. So that could be a decrement as well, because you no longer observe that particular life. And sometimes a healthy person can become sick. And if sick is not in the model, one of the states in the model, then that would be a decrement. And again, other times you can also classify states as the decrement. So again, it just depends on the way you try to use these particular words. But somewhere specifics will be related, and we'll see how that comes about. So first of all, some terminology. We will define the future lifetime of a particular person as T. So what I'm trying to do here is I define T as a random variable, which from now on I will say denotes the future lifetime. So this thing denotes the future lifetime. of someone that we don't know yet. So again, this T actually denotes the future lifetime of a newborn baby. And why do I specify in brackets that this is for a newborn baby? Because not every time, whenever we as insurance company have to get policy holders, we don't always get people who are newborn, right? I mean, most generally these will not be the people we get. So they will be aged X sometimes. So this TX just denotes a random variable where a particular person has already attained the age of X. So this will just denote the future lifetime of a person aged X. So I can clearly see that this is something that is much more useful to me because, so I mean, I can again just say that this is T0. It wouldn't really matter much. So this will be the future lifetime of a newborn baby, and TX I denote as the future lifetime of a person aged X. Okay, and now for our calculation purposes, because we are looking at t as a random variable, we want to see what is the minimum value that t or tx can take and what is the maximum value that these can take. And just to specify that, we say, again, we know that, if I'm saying, okay, so also remember t is the future lifetime, not the age. So the minimum t that you could ever have is 0, because you can see that the person is alive today and he's going to be dead in the next second. So the future lifetime for that one particular person would just be 0, or it could essentially go. So again, it's nice if we can say that it can be till infinity, but we know for sure that after a particular age, people are no longer they no longer have a great chance of being alive. So we cap it at certain number, which we denote as omega. So we assume that this omega is the maximum age. So again, I guess it is mentioned in your books that the typical value of omega is generally somewhere between 100 to 120. So sometimes this might also vary depending on the policy that you take. Sometimes in policies themselves, they do not insure you for the whole of your lifetime. They might just insure you till you reach a particular age. So then for them, it would be easier to just cap your lifetime here. But again, I guess there will be some probabilities and everything else that will be affected. So this decision has to be made by the modeler himself. And this is what we call as the limiting age. So this W is the maximum age that a particular person can achieve. So now if I'm saying that I'm looking at TX, then I know for sure that this guy has already attained age X. So X years of his life are already being lived by him. So the future lifetime for this guy will be from 0 to omega minus X. So because I'm measuring the future lifetime and this omega represents the maximum age, and I know for sure that this person has already lived for X years. So I know that the future lifetime X years, to get its maximum value, I have to subtract the X years. So I would essentially subtract X years from here as well. But again, this is just 0 and negative does not make any sense. And even if you just think about it logically, I think 0 is what you will think of at first. So this is about the domain of T, which is kind of representing time here. But again, time and one time unit is 1 year, let's say, of age. So that's it. And now this is the random variable that is our concern for this particular chapter. So we'll try to figure out its distribution function, and it's way easier. I think it's much easier for us to figure out its CDF. So if I say f of t, this in essence just represents probability that this random variable will take a value less than or equal to t. So if I were to see this in terms of words, this t I know is the future lifetime, right? So this just means the probability that a newborn baby will live for less than t years. So this is just f of t, which is kind of the CDF of the random variable t that we are looking at. And so this is about the probability that this person will not live for more than 3 years. But this whole subject is about survival model. You want to check the probability of this guy surviving. Or, I mean, these are mutually exclusive. So if he does not survive, he's dead. So another thing that you can have a look at is S of t, which is known as the survival function. So would anyone want to guess? How can I write my survival function using this t random variable? So basically, if I want to convey that what is the chance that this particular person who is a newborn baby will be alive for more than t years, or will be alive for at least t years? What do you guys think should come up there in the bracket? Anyone? So what I mean by Sx is the chance that I will observe a particular person being alive for at least t years. And by the t years, I mean this small t. So how do you think I can represent it here using something like this?
T greater than equal to small t.
Exactly right. It will just be t greater than or equal to small t or greater than t. I mean, it doesn't really matter much. Because if we assume that this is a continuous function, then yeah, it just fades off. So this can be written as, so now if I mean, just to be strictly adhering to what's there, I'm just going to write it as greater than. Okay, so this is nothing but just 1 minus f of x, f of t, right? We have t here. Okay, all right. So we have 1 minus f of t as the survival function for t guy. So similar thing we can do for the tx random variable as well. And what you will have is, you just write a small x here, you will just write another small x here, and now instead of t, you will have tx. So here what you're trying to do is just figure out the future lifetime and survival function for the person who is already aged x, and you already know that. So this fxt here will in a way represent the probability that a person aged x dies in next t years. So you can also say that this person dies before the x plus t age of his, or you can say dies in next t years. So this would essentially mean the same thing. So I would say one important thing from here is the survival function. Okay, maybe I shouldn't do that. I'm just gonna leave it at that. So this is how you would write the CDF. But again, now we have just written it in terms of probabilities. We'll try to see how can we elaborate much more on that particular thing. So now when I'm talking about FXT, I have my FXT, which is nothing but the probability that my TX takes a value less than or equal to T. So again, here I'm looking about not the survival function, but the chance that this person will die before he attains the age X plus T. So if I have this thing, what I can do is I can rewrite this distribution function of capital Tx random variable in terms of the T random variable. So what I can do is I can probably change this guy. So the probability that Tx will be less than or equal to T is equivalent to saying that a newborn baby should be alive for less than or equal to x plus t years of age, right? But I should never forget that I'm conditioning on the fact that this guy has lived up until x years of age. So because if I say t is less than or equal to x plus t, it might mean that t is equal to x minus 1, right? But we know this is not true because our t is greater than x for sure, but less than x plus t. So to take that into account, you will have to write this conditioning on the information that you were given. So once you have this, you can also just use the Bayesian formula. So what you will get here is the probability that you observe t being greater than x and less than or equal to x plus t upon the probability that you observe t being greater than x. So again, I think it's just much more convenient to again
Ma'am,
rewrite these in terms of capital. Yes.
uh, I had a network issue for a while. Could you just explain what you did in the second step?
Okay, so in the second step, I have rewritten the Tx in terms of T. So remember, T is for a newborn baby. So when I say Tx, I mean that I have lived up X years of my life. So when I'm writing this probability in terms of T to just be consistent, what I'm doing is I'm first of all saying that this T should be less than or equal to X plus T. But I also have to take into account the fact that this T will be greater than X for sure, because it can't be less than X, even though we are seeing that this is less than x plus t. Does this make sense to you?
Yeah, okay, got it.
Perfect. So then I'm just using the Bayesian formula to rewrite this probability, and now I'm just rewriting this as f of x plus t minus f of x upon, so I can again rewrite this as 1 minus f of x. Does this make sense to you guys? So again, I've already seen 1 minus f of x is nothing but survival function. So I can also rewrite this thing as s of x. So remember, because now I have everything in terms of t, I am not writing x subscript here or here. So because it's in terms of t, I have plain f and I have plain s. So I just hope this is clear. So again, from what we have studied previously, we know for sure that these TQX represents the probability that if a person is aged X today, that he'll survive, that he'll not survive by the age X plus T. So this is nothing but F of subscript X small t. And when I'm talking about TPX, this is nothing but 1 minus TQX, as they're mutually exclusive. And again, this is just equivalent to the survival function. So I have Sxt. So remember, this t here is what I have here, because this is what I am comparing my future lifetime against. And this x here represents the age that I have already attained. So these are two important formulas that you will just have to know. I mean, I think it's just convenient, and I think it's pretty straightforward for you to remember as well. This is survival function, and this is the probability that you die. So before you reach the age x plus t. Okay, so now let me just ask you guys a very quick question, which will involve a bit of just logical thinking, nothing of this sort, but just understanding of what these formulas mean. So if I write these two probabilities, 5p34 and 7p33, if I tell you guys to compare these two probabilities, which of these do you guys think will be higher compared to the other one?
5p34 will be slightly higher.
So Isha says this is higher, and why do you think so?
Because this means that the person is aged 34 right now, and the probability that he will survive for at least 5 years.
Yeah.
Will it be at least or exactly 5 years?
It will survive for at least 5 years. This is all you can say, right?
Okay. So I think that will be higher because there is a condition of lesser years for surviving more, and uh, as the age keeps on increasing, the force of mortality will also increase, right?
Okay, so if I tell you the force of mortality is constant, then will your answer change?
No, again because there are lesser years in consideration.
Exactly right. So again, just on the very basis that here we are only looking at 5 years and here we are looking at 7 years. And again, these years are incorporated in these years, right? This starts at 33 and ends at 40. This starts at 34 and ends at 39. So here I'm talking about leaving from 33 to 34 and being able to again be alive from 39 to 40 extra than this particular probability. So again, you would actually see that this probability will be very, very less, because again, the chance that you will survive will for sure not be 1. So whatever you have here is again just getting multiplied with some 2 numbers, which is less than 1. So this would be a technical analysis. But again, rightly, if you just observe more number of years and not only more number of years, but also encompassing this, then it just makes some logical sense to just conclude directly that yes, this would be higher and this would have a lower chance compared to each another. Okay, good. So again, just one more technicality. I think this we have already studied. So just to remind you guys, if I'm talking about annual rates, so this can be just, mortality rates. So if I'm talking about the annual rates, if I have this thing, I can just write it as QX. I do not write one QX. And if I have one PX, I just write it as PX. This is for convenience. And again, because in actuarials, we will more generally be looking at what happens within a year. So this is just some shorthand. So QX will be the probability that a life who is aged X today will die within the next year. And the same for this guy, just the probability that this person will still be alive up until the next year. And so actually good question, Aisha. So when I'm talking about 5P34, all I can say is that this person is alive up until the age of 39. I cannot say if he dies after that, if he does not die after that. All I can say is that he's at least alive for 5 more years after being 34. So that is all you can conclude. But again, now we know that if I'm, let's say, looking at the instantaneous rate of mortality, I denote it as mu. So this mu of X here, this represents the probability that you will die, let's say, within the next second or something, within the next instance. So I am just, so if I were to just write this in using limits and everything, I'll get that H going to 0, 1 upon H probability. So again, now I'm trying to use the formulas that we have seen. So T being less than or equal to X plus H, given that T is greater than X. So this is, again, we have mu X here, and that is why we have taken this X into consideration, that the person is already attained, and the person has already attained the age X. And now we're trying to see what is the chance that this person will die in the next instance. So remember, we're just looking at a small increment in X here, which is H, and this H need not be an integer. It can be a fraction as well. So need not be 1 year or 2 years. So this is the formula that we have already seen. And again, if I just basically, I know that I can rewrite this thing in terms of Qs. And what this will become is H Q X, right? And I have something like divided by H. And then if I just ignore the limits, I get mu of X here. And this we have already seen again, but just, so if I just take this H from here onto the other side, what I get here is this thing times H. So if I'm saying that mu X is the mortality rate for one particular instance, and if you're looking at H time, then I'm just multiplying what can happen in an instance with the time units that I have increased here. So let us say if you're given about the mortality rate for an hour, and if you want to figure out things for like a day, then you will just multiply that mortality rate for an hour with 24 to arrive at the day's mortality rate. So I guess that is just something that, again, I'm just revising. So this is something that we have already seen. So if you guys remember the PIJH that we used to study in the previous chapters, I used to take H times mu II or mu Ij, right? So that was again just something similar to this precisely. Okay, so again, there are some technical issues and some theoretical issues when we try to figure out the value for this mortality rate or this HQX, this which is the probability that you will die in a very, very small interval H after you have attained the age X. So, I mean, some of them being just that, these probabilities may not correspond. I mean, so the kind of H that we look at sometimes, let's say if you're talking about the year, you might ignore that it's a leap year, or if it's not a leap year. So the number of days that you will have in a year precisely would not be 365. It would be a bit more than that. So that you'll have to take into consideration. And again, this H, we are seeing it tends to 0. So to get to the formula, I've ignored the limits. So that's also there. And again, I think this is just very tricky to figure out from the data itself. So, but we have already seen how do we figure out the values of mu, right? Which is the mortality rate using some data that we might be given. So we'll just try to look at that again from if, let's say we have some another kind of data which is provided to us. And once we know the value of mu, we can easily figure out the value of someone being dead or someone being alive for so and so years. So again, before we do that, let me just rewrite the equivalent definitions of this mu x. So again, there are two ways I can rewrite this definition. I can rewrite this in terms of t, or I can rewrite this in terms of tx. So this is what I have in terms of t, and now I'm going to rewrite this in terms of tx. So again, if you see, I'm taking mu x plus t. Here, if I would have had x plus t, then what you will have here is x plus t here as well. So let me just do the same thing again for now. So this is with t. So again, wherever you have x, you would have x plus t here and x plus t here. But now if I'm doing this particular thing in terms of tx, then how would it look like? So I'll have limit h going to 0 plus again 1 upon h. Yeah, but now if I'm talking about the probability, I know for sure that this guy has lived up until X years of age. So how much more do I want him to live? T plus some H. So I see that, so again, I'm not talking about the survival, I'm talking about a particular mortality rate. So I will have a less than or equal to symbol, and I'll have T plus H here, given that this guy survives 40 years. So I guess because we have mu x plus t, I know that this guy survives up until t and then dies in the next moment, right? Because whatever I have in the subscript of mu is when I expect this particular person to not be alive anymore. So what you will have here is tx being greater than t, not being greater than x plus t, because tx is already taken into the fact that you are alive for x years. And now you just need to be alive for t more years and then be dead in the next moment to arrive at the value of this mu x plus t. So again, maybe I should write the heading here. This is the force of mortality. And again, instantaneous. All right. So these are just, I'm just going to go through this stuff in today's lecture. And in the next lecture, we will see how do we have particular models and how we will go about figuring stuff out when we have the actual data. Okay. So now again, coming back to another way we can actually write survival probabilities. So if I'm, let's say, talking about sxt here. What do I mean is that I am alive. So again, coming back to our favorite number line, we have a x here. So I know that the person is alive up until x. And what I expect is that this person is alive for x plus t years, right? So whenever I'm talking about sxt, I mean that this person is alive from here till here, right? So what I can again just so this can again be rewritten as tpx. So I can just say that this is nothing but tpx. So now let's say if I want to figure out what is the chance that this particular someone will be alive for more than t years. So again I just write s plus t px. So what I know is that this person is alive up until X, and I want to figure out what's gonna happen to this particular person after S plus T years. And I want him to be alive, which is this particular probability that I'm trying to figure out. So if I'm talking about this S here, let me just write X plus S plus T here, so that this particular could represent the S, and maybe I can have some X plus S in between here. So if I'm, let's say, writing about the duration, I can maybe say that this much is my S, this much is my T, and again this much is again my S, right? Because the difference is just S. So this is about the duration. Yeah, but again this, whatever I have on the axis, is the age. So there again, so what I'm trying to say is I start at X and I find myself alive at X plus S plus T. So what you can do is you can have the probability that you're alive from X till X plus T multiplied with this thing. So if I were to rewrite the probability that I will start here is X plus T, and I'll find myself alive here, which will be X plus S plus T, right? Does this make sense? I want you all to see. So I've made a mistake deliberately, and I want you all to see what mistake I have just made on the board. Why I couldn't hear you?
It would just be F, right?
It would just be F.
F.
S, yeah, right. It would just be S because I'm talking about how much more I expect to live after I have lived for X plus T years, which is just S here. So this could just be, TPX times SPX plus T. Or we can also look at it in different manner. We can say that I'm alive from here to here, and then I'm alive from here to here. So this would be what? PXS, and this would be P x plus s t. So again, this can also be written as spx times px plus s. So these are just different ways you can rewrite the probabilities. So sometimes you might be given some information and you might have to just, write down these two equations for the similar probability, and then you can maybe figure out these unknowns if these are unknown, and if you know the value of this particular guy from these other guys. So this was just about the survival probabilities. All right. So up until now, what we saw was what happens if we have capital T less than or equal to T, or if we have capital T greater than T. But sometimes we may also want to know what is the chance that this person will precisely be dead at this particular time, or this person will precisely be alive at this particular time. So for that, we will have to look at its PDF. So up until now, we saw the CDF, but now we also want to look at the PDF. So the way I will do is, again, we know that if I differentiate the CDF, so basically if I have fxt, and if I differentiate this guy with respect to t, I will get my PDF, which is just small f of xt, right? So the way I'm going to do this is again use the first principle formula of differentiation. So when I have this guy, I know I can again rewrite this particular fxt as d by dt probability that I observe tx less than or equal to t. And then I can again rewrite this using the first principle formula. So first I have limit h going to 0, and what I have in the numerator is plus h with this guy. So probability that tx will be less than or equal to t plus h minus the probability that I will observe tx being less than or equal to t. And this will be divided by t plus h minus t, which is nothing but just h. So if I again take this forward, what I can do here is, because I have tx, I can rewrite this whole term and this whole in terms of t, capital T only. So I want you all to tell me what will come here. So if I want to rewrite this particular probability in terms of capital T and not tx, how can I rewrite this thing? Anyone?
Probability of t less than equal to x plus t plus h
Yes.
minus probability of t less than equal to x plus t.
Are you sure about that, Mihir? So can my t here be less than, can my t here take a value x minus 1? So I know that my t is still less than x plus t plus h. But can my t be less than, can my t be x minus 1 here?
No one.
No, right? So I know for sure that my t has to be greater than x. So I cannot forget this conditioning here. So my t has to be greater than x for sure. And then I will subtract the remaining term, which is again the probability that my t will be less than or equal to x plus t, given that t is greater than x, and divided by h as it is. All right. So now once we have this, we are just going to try to simplify this thing now. So h goes to 0 plus. I'm going to use the Bayesian, and I can clearly see that in the denominator, I'm going to have the same stuff. So maybe what I can do is I can just rewrite this thing as f of x plus t plus h, or yeah. And so what I'm doing is, okay, maybe I think I should do it stepwise. Okay, so if I have this, I know I can rewrite this thing as, okay, maybe I should just do it here. So I can rewrite this whole particular term as, probability that my t will be less than or equal to x plus t plus h, and that it is greater than x, upon probability that my t is greater than x, right? And this thing is nothing but the survival function for x. So again, no x here, x here in the brackets here, because we're looking at capital T, and x is the value that we're comparing it against. And for this guy, what you will have is f of x plus t plus h minus f of x, right? So this is what you will have, and then s of x is what you will get in the denominator. So I'm going to use this to rewrite this whole equation here. So again, what do I get here is f of x plus t plus h minus f of x, right, which you get from here, and minus f of x plus t minus again f of x. And I'm going to take the same thing in the denominator here, s of x and h simultaneously. So now there is a little trick that I'm going to use to simplify my equation. So I will multiply and divide by s x plus t. So again, this s of x does not depend on h. So I'm taking it outside and I'm multiplying this with s of x plus t. So what do I have now is again limit h going to 0 plus. So now I don't have s of x in the denominator. Instead, what I have is s of x plus h. And again, this is what? This is times h. And this will be as it is. But if you see this f of x and this f of x will get cancelled. And all you will be left with is this. So you will have f of x plus t plus h minus f of x plus t here. So if you have a closer look at the numerator now, do you guys see something familiar? Or let us say if you have a look at this. So if we have a look at this, what we have just seen, okay, I did not specifically write it. So maybe what I should have done here is again, so if I try to rewrite this thing, I can just say that this is probability that my tx takes a value greater than t. And again, I can rewrite this in terms of t, which is just t being greater than x plus t, such that it is greater than x for sure. And this would boil down to the probability that you observe a value of t being greater than x plus t, right? Because if t is greater than x plus t, then I know for sure that t is greater than x as well. So this is just upon probability that t is greater than x. So this is nothing but s of x plus t upon s of x. And this is what we have in the coefficient for our limit guy. So I can easily substitute it for s of x t. So this, whatever I have here, I can rewrite this guy as s x t. Okay, so now can I do something similar with what I have here? Have we studied any relationship up until now that we can use? So I think this is a bit much more difficult to see than the other ones. But if we have a closer look at the way we wrote this particular function here. So we have this 1f. Yeah, I think it's easier to see here. So we have this 1f here and then another f being subtracted and upon s of x, right? So this s of x is precisely what I'm subtracting this particular thing from. So if I have x plus t here and I have s of x plus h, no, this should be x plus t. Yeah, it should be t. So basically, if I have the same thing up here and down there, then I can see some correlation between these guys. And then I can easily try to see if again I take my h outside of this guy and I just write it somewhere here. So maybe I'm just going to write it here, 1 upon h. I can see that this is equivalent to what? So this whole term is actually equivalent to this thing, right? And what was this thing? This was something just like the probability that you observe a t, which is what you started off with. So this, so the thing that we did in orange was for this guy. All right, so we will have something similar to this now. So again, x plus t plus h is whatever you have here. So this will be less than or equal to x plus t plus h such that t greater than x, and that is what you have in the denominator. So here you will have t greater than x plus t. So this is what you have for this particular value that we observe. And now again, if I were to just simplify this whole thing, I will have s of xt getting multiplied by what? By limit that my h goes to 0 plus 1 upon h, the probability, this whole thing. So t being less than or equal to x plus t plus h, such that my t is greater than x plus t. So now if you observe this particular thing closely, this is the instantaneous rate that you die at the age x plus t, right? So this will just become sxt multiplied by mu of x plus t. And that's it. This is your PDF. This will be the probability that if you are aged X, you will be dead by next T years. You will be dead, in next T years. So this is what you will have. And again, I know that I can rewrite this as xt in terms of tpx. So I can also write this as just tpx times mu of x plus t. And this will be what I have for f of xt. And this is kind of important result, very important result. And there are so many questions that do get asked where you have to utilize this particular information. So now again, just to be comprehensive, this is not valid everywhere, but only for the cases where you have a value of t that makes sense, which is for all of these cases. So this is omega minus. So what we have here is omega minus x. Why? Because I'm looking at x years already passed. So again, this is the kind of model that we have started. So this thing will try to answer, what is the probability that a person will die precisely t years from now when he is aged x. So this is what Aisha, I guess, was trying to ask. So yes, now if I'm trying to figure out the small f, what I'm looking at is that my capital T is indeed just equal to small t, right? No more less than or greater than stuff. So I know that my life will precisely die t years from x years of his age. So this is the PDF of EX. Very important.
Hello, ma'am.
Yes, Vanshita.
In the step after the star, please.
Can you speak up a bit louder? I could only hear star.
Yeah, can you explain the step after the where you marked star? So can you please want to explain that how did
Oh,
the
okay. This you mean?
Yes.
Okay. So this star here actually corresponds to what I've written over here. So if this is only one term that I've considered, which is the Bayesian probability. So this thing can be written as, the probability that my t takes a value greater than x and less than this thing. So this is the intersection upon the probability that t is greater than x. And this thing I can write as s of x, which is my survival function, right? Because t is the future lifetime. And I'm talking about the probability that I survive for at least x years of age. So this is s of x, and that is how I get s of x. And this denominator here is common for this guy as well as this guy. So I've just skipped that step where I write those separately and written them down in the denominator simultaneously for both of them. Does this make sense?
Yes.
Okay, good. Any more doubts? Anyone else? So now maybe what we can do is you all can try to open up the formula booklets that you have. And if you go to page number 68, 69, you will see some tables over there. Do you all have the formula booklets with you? Or I can also just send a picture in the group. Let me just do that for. Yeah. So now if you have a close look at the table, and if you try to see what we have is, we have some x here, and that goes from 0 up until 109. right? Not beyond that. So this is, again, this is for males, and in the upcoming pages, you also have this thing for the females, and that goes up until 112. So that must have been some observation of these people. We don't know, but yeah, it goes on up until 112, and this thing goes on till 109 for males. Okay, so what we have here is some Ix, Dx, Qx, Mux, and Ex, a circle up there. That's not a mistake. There is indeed a circle up there, and it has some rationale that I will explain soon. So this X is nothing but the age, and this X represents the age of a particular English male, because these are English like tables. And what is my Ix? Does anyone know what is Ix here?
It is LX, right?
LX.
Small LX.
Oh yeah, it's Alex. Yes, it's Alex. Sorry, yeah, it's Alex. What is my Alex here?
It is number of lives alive at age X.
Exactly. So this Alex here represents the number of lives that are alive for a particular corresponding age X. And if I have dx, it represents the number of people who have died in the age X. So when I say in the age X, it means that they died from age X to X plus 1 and somewhere in between X and X plus 1. So if I have dx for, let's say if I have d3, it represents the number of people, it represents the people who have lived up until 3 years of age, but then died before they could reach the fourth year of their age. So that is my dx here, and I guess you guys do know what is qx. So again, there is no t there, and this is just for 1 year. So the probability that this particular person aged X will be dead within 1 year. And mu X again is just instantaneous rate of rate of each person aged X being dead. And then we have EX circle that represents some expectation, and we'll see that soon what that is. So for now, this is all I wanted you all to see from the table booklet. And now what we can do is we will try to see some connections between these values that we are given in the life table. But sometimes, so if you have a look at the table, they don't tell you what is the chance of person being alive, right? We know only the chance of the person being dead in the next year, and we know how many lives are alive at each particular age. So we'll try to figure out some sort of a relationship between these values and variables so as to give us the answers that we try to pose questions for. So the very first question that we might have is, what is the chance that a particular person will be alive next year as well? So the very first thing that comes to my mind is rather just 1 minus qx, right? So this is what you can do, and if not this, the other thing that you can also do is you can use actually the number of people you know are alive at each particular age. So what is my px? My px denotes the probability that a person will be alive by his age x plus 1, given that he is already alive up until the age x. So this can also be actually calculated as L of x plus 1 upon L of x, right? So this is the number of people I have alive at age x, and this is the number of people I see alive after 1 year. And the probability is just one of the estimates, and this is a very good approximation to my 1px here. So what again I can do is I can just use this particular thing to calculate my qx, because let's say if you were not given the value of qx, then what you will have is that my qx is nothing but 1 minus px, and then what you will have here is 1 minus L of x plus 1 upon L of x. And this I can write as L of x minus L of x plus 1 upon L of x. So now if you guys have to see, what could this numerator mean here? So Lx is the number of people I have alive by age x, and x plus 1 is the number of people I have alive by age x plus 1. So the difference in these is obviously the number of people who died in between x and x plus 1, right? Which is what I denote by dx. So I have my dx upon Lx. And this is nothing but Qx, the probability that you will see people being dead. And this is, this confirms our intuition, right? This is the number of people you expect to be alive by the age of X. And these are the number of people you expect to die. And these are the number of people you expect to still see alive. And that is why this figures out Px, and this gives you Qx, respectively. And now again, this was a simplified case. And if you were looking at Tpx, what you will have is L of x plus t. So instead of x plus 1, you will just have L of x plus t here. And similarly, if you try to do this thing for the tqx, instead of this 1 here, you will have t. So this will just be Lx minus Lx plus t upon Lx. Okay, so now you can't necessarily say this is dx because we don't know how many people are dead in between here. But maybe what you can do is you can just sum up all the dx's, right? Which will be the number, which will be the sum of all the people who might be dead in between x and x plus t. So that is something that you can do if you have that information. So this is the kind of information that we will generally have, because we know how many people we observed initially, then we know how many people we are observing at the end, and we know what happened to the people we didn't observe up until the end. So whether they died, or did they leave the policy, or did something else happen to them, or something. So these are the kind of probabilities that we concern ourselves with. And yes, this is how we will try to figure out stuff. Okay, so now when I'm saying that my dx is representing the number of deaths that have occurred for people aged between x and x plus 1. So I know for sure that when I observe deaths of people, so let's say if I'm observing people over 1 year, and if I start with 50 people, and by the end of the year I only have 49 people. Okay, so 1% died in between the observation. So when I'm talking about my approach to figure out how much of the risk, how much of these lives were exposed to risk for. So let's say if I have to figure out the time these lives were exposed to risk for, then I would have some confusion, right? Because if I know the precise day or date at which this particular life died, then I can figure out in terms of fractions as well the number of the times I have observed people, right? Because the total time I have observed people, the total waiting time that I have. But sometimes you may not know the precise dates. Sometimes you may not, let's say if a person is dead, this is not the first thing that people will do and call up the insurance company, right? So it might take them like 13 days or something. So you never know what is going to happen when. So there are the discrepancies, but there are certain assumptions that we'll make, and then we'll try to see what happens. So again, when we try to figure out the rates of mortality, there will be two different ways that we can use. So sometimes we just assume that these deaths happen uniformly over the year. So let's say if we have certain number of deaths, then we see that these have happened with equal probability over all of the year that we were looking at. And the other times you can just assume that this force of mortality remains constant throughout. So this mu does not change with x, and it just remains constant. So let us see what happens in the case where my u is uniformly distributed. So let us say if I have a uniformly distributed mu. So again, not uniformly distributed mu, but uniformly distributed deaths. So I'm trying to figure out, so instead of just taking the actual time when the people were dead, what I do is I put a particular assumption and I assume that all the number of deaths that happen are uniformly distributed over the time interval that I'm looking at. So let's say if you are looking at x2 x plus 1, then you can just say that this, so again, I mean, let's say this is the time interval that you concern yourselves with, then you will have to see what is my tqx and what is my tpx value. So here it's a very intuitive result because we are assuming uniformity. This just happens to be t times qx, and this will again just be 1 minus pqx. And also you can write this thing as t times px, I guess. So again, you can actually derive this relationship here using something known as interpolation method. So it's precisely known as linear interpolation because what we do is we make a linear interpolation. So again, what do I know? I know what has happened at, so this life will be aged x and the life will be aged x plus 1, right? So I know how many people I have observed here and I know how many people I have observed. Hello, can you guys hear me?
Yes, ma'am, now we can.
Okay. So I know I observe people alive at age X, and I know how many people are alive at age X plus 1. But let us say something happens in between. So let us just denote that time as X plus. So let me just denote that time as X plus T. So again, I'm making an assumption that my T lies in between 0 and 1. Okay, so this is the assumption that I'm making, and the number of people alive here, let's say just I denote them as L of x plus t. So now if I want to figure out how many people are, dead by the time t, so, or basically just to know how many people are alive at time t, even if I haven't observed this particular thing specifically, so what I can do is I can assume that there is a linear relationship between these guys so that the slope of these guys are the same. So what I do is I use linear interpolation. So many people try to remember the formula, but again, I don't even know a way to remember the formula. But what I just do is this thing. So what you will have is L of x plus 1 minus L of x upon x plus 1 minus x. So this is one slope that you have for these 2 points. And then you can take these points or these points to figure out the slope and have the unknown quantity that you want to figure out in the equation. So I can just write minus Lx upon x plus t minus x. So these would cancel and these would cancel. So I have a t here left and that I'll take it here and then I'll have a Lx here. So if I have to just write my Lx plus t, what I have is t times Lx plus 1 minus Lx plus Lx. And I can again just simply rewrite this thing as Lx plus 1, right? And I have minus t Lx plus Lx. So this can just be plus 1 minus t Lx. So this will give you a very good approximation for the number of people you will have alive by the time x plus t. So sometimes this is what you will use. And now given that we have already derived this, what I can do is try to prove this relationship. So what I will do is just write tqx, and from previous, I know this is nothing but 1 minus tpx, and I know that I can write my tpx as L of x, so t, so x plus t upon L of x. And now what you will try to do is again, you will have Lx up here. So, but again, I guess, yeah, you can just do that. Lx minus Lx plus t upon Lx. So now we don't know anything about Lx plus T, but we do know that this is the relationship that it does satisfy. So Lx minus T Lx plus 1 minus 1 minus T Lx. Right? So this Lx and that Lx will cancel each other out. And what you will be left with is T times Lx minus Lx plus 1. There's no upon. Oh, there is upon Lx. And this everything will be upon Lx. And now, as we know, what is this? This is just 1 minus Lx plus 1 upon Lx. And I know what I can rewrite this thing as, right? This is nothing but T times 1 minus Px. And this is nothing but T times Qx. And that is how you do derive this particular result.
Ma'am,
Yes, Mihir.
the second equation you have written for TPX is equal to T into PX, right?
Tpx. Yeah.
But I think it doesn't hold true for surviving probability.
It doesn't hold true? Okay, yeah, I think I did say maybe over there. So yeah, I haven't quite derived this. So yeah, thank you very much for letting me know. I don't know if that holds true or not. But yeah, well, I can just do it for this particular thing. Okay, for survival, what will we have? Oh yeah, we'll just have this particular thing, right? Not 1 minus. So you'll just have something like this upon Lx. Yeah, it doesn't make sense, right? So you will just have this thing upon Lx for PPX over here. So, okay, thank you very much, Mihir. All right, so any doubts with this? Okay, so here what I did was I assumed that my dates are uniformly distributed, and which is why I could use this linear interpolation. Right, because I've assumed that the slope in between these two people is same as the slope in between these two people. So that is what I get as a result if I assume that deaths happen uniformly over the year that I'm concerning myself with. Okay, but now we also discussed that sometimes that is not everything that we need to know. So again, whenever I'm talking about, let's say, Qx, or if I'm talking about mu, this is called initial rate of mortality. Maybe I should write it here. So this is called initial rate of mortality. So we have two concepts of mortality. One is initial rate of mortality, where we do use this Qx and mu x and all of this stuff. So this is one. So again, the formula for this guy is what? We have the number of deaths that we observe in particular year upon the number of lives alive at age X. So this is what we have for the initial rate of mortality. And we assume that, deaths happen at the age before X plus 1. So number of deaths between X and X plus 1. So this is what we have. But now there's another concept of mortality that we can study, which will try to measure the precise mortality rate. So here we made some assumption about the deaths that we observe. In the next rate of mortality, which I call as central rate of mortality, what I do is I try to measure the precise mortality. I try to measure the precise estimate of the mortality. So I take into consideration the precise time when I observed a particular person being dead within the time interval. So again, we are looking for 1 year. So this will be Qx upon integration from 0 to 1 and then just Tpx dt. So this might seem a bit, I would say, weird now, but if we just have a look at this formula, this is nothing but I think the most intuitive way to interpret this particular equation is to rewrite this qx. So if I see, what I can do is I can kind of rewrite this particular qx as integration 0 to 1 tpx. So what I'm saying is that I started observing a person at age x and he is alive by the time t, but then he dies at x plus t. So this is precisely what you will be observing at qx. But again, the reason I can write t here is because I'm restricting my t from 0 to 1, and because I have 1 here, right? So again, this is true, and divided by integration from 0 to 1 tpx dt. So now if you see, this looks like a weighted average of tpx. So this is the weight. So this mu x plus t, sorry, this tpx is the weight that you're assigning, right, for each mu x plus t. So for each particular mortality rate that you try to figure out, you're assigning this tpx as a weight, and then you try to sum them up across in the denominator to get to a weighted average for the force of mortality for the next year, because again, we are only looking at from 0 to 1. So this is denoted by mx. So this was mu x, and this we denote by mx, which will say the probability that you observe a particular life dying between the age x and x plus 1. So that's it. And here what we're trying to measure is the actual precise rate of this particular person dying. So here we don't only consider how many people were alive at the age x. Here we will try to see how much, for what is the total time we have observed people for. So for how much of time these people that we observed were exposed to the risk of being dead. So the number of people who died, so the number of deaths upon the total time spent being exposed to risk. So when I say being exposed to risk, the risk I'm talking about here is the risk of being dead. And that is why what we will have here is the total number of time that you have observed particular people. So let us say if one life dies after 6 months, then the total time spent being exposed to risk will not be. So let us say if you're looking at, some, okay, let's just take a very precise example. Let us say again, we are starting at 50 and we are looking at people from 50 to 51 age. All right. And now we see that we have, let's say, 100 people in our experiment. And one of those, did I say we have 50 people? Yeah. So if we have 50 people, one of those people die. And by the end of it, we only have 49 people, right? So if I know precisely that this particular person died after 6 months, then my initial mortality rate will consider what? It will consider 50 in the denominator, because that is the number of lives we had alive by the age of 50. By the age of 49, because we are looking at, let's say, oh no, did I say age 50 or, okay, so again, we consider 50 people and we are looking at their lives from 70 to 71, let's say. Okay, so we have 50 people and 49 of those people are alive by their 71st birthday, by their 71st birthday. Okay, so we have that. And now if I'm talking about the initial rate of mortality, to figure that out, what I will have in the denominator is the number of lives alive at the age of 70. So that will be what? That will be 50. But now if I have to figure out the central rate of mortality, in the denominator, I will have total time spent being exposed to risk. So how much of time these people in total have spent being exposed to risk? So for 49 people, it was 1 year, whole of the year, right? But for one person, it was only half the year. So you will have that. So 49.5 is what you will have in the denominator instead of the whole 50. So that is the difference that you will have in these two kind of ways. You can actually figure out the rate of mortality. So this MX is actually pretty popular, and we'll again try to see how we adjust this particular value of MX. But again, we'll try to see if we can get some relationship between the MX that we think is much more precise and the MUX that we think is much more easier to calculate. So if we try to do that, what you will have here. So again, what will help us is that we have this QX here. And again, if you just see, you already have a relationship, right? You have a MX here and you have MUX plus T here. So that is what you have. I think that's really cool. So oops, you have MX here, and this is the whole formula that you have. Okay, right? So now this mu depends on T, and let us just assume if this does not depend on T. So if my mu is a constant, then what will be my mx? I know that this, if mu is just a constant, it will come out, and I'll have the integration 0 to 1 tpx dt upon integration of 0 to 1 tpx dt. And these will just cancel each other out. And what I will have here is that my mx is nothing but u. So there is no difference if my rate of that is constant throughout and it does not vary with the age. So I see, I mean, there is some really nice connection that we see. So we know how we can write qx in terms of mux and so and so, and now we know how to write mx in terms of mux plus t, and if it's just a constant, it's equal to mu itself. Okay, so I hope this is making sense to you guys. Any doubts so far? Anyone? Any doubts? All right. So again, today we are just going to cover these notations part and blah, blah, blah. Okay. So now what we will try to look at is something that we started the lecture with. How much do we expect people to be alive for in future, right? So from the time today, we want them to be alive for, I mean, we just want to figure out the probability that these people will be alive or dead sometime in the near future. So this is what we will try to figure out now, and this is where the EX circle thing will come into picture. So now so again, I cannot precisely determine this thing, right? I'm using estimates and I'm using the sample that I have observed. So what I will try to figure out is the expected future lifetime. So this is something that we concern ourselves with now. So again, if I know that some particular person is aged X, then this is what I want to figure out. All right. So again, we can just simply use the formulas that we have just studied to figure out some relationship, and then try to study a way to figure out this expected future lifetime. So what I want to do is, I don't want to sit and derive this everything here. Maybe I'll just share this, and yes, I'll just try to do it from here. Okay. So yeah, so this complete okay, whenever I'm talking about expected future lifetime, there are again two ways to figure this thing out. One is a very precise way, which is the complete expectation of life. And the other would be, let's say if we look at the discrete ways, let's say if we do not consider the ages in non-integer terms. We only consider from age X to X plus 1. We don't consider what happens in the between. So then it would just be called curtailed expectation of life, because you're curtailing the values that your age can take in between X and X plus 1. All right. So whenever you're talking about complete expectation of life, this O, you have this circle. So yeah, this is read as E circle X. So this is how you will denote your expectation of Tx if you're looking at the complete expectation of life. But again, what is my complete expectation of life? So if we again just try to bear ourselves, there is some integration stuff. But again, this is not much difficult. So let us first try to see what they have done here. They have just derived a relationship between something we know. Okay, this is what? Can someone tell me what is this in words? What does this blue box term represent in words?
Probability that the life age X will survive for T years and then die instantly.
Precisely, right? Okay, so we just derived that this is nothing but our PDF for the P guy for the future lifetime. This is what we got as the PDF of this guy. So now if I want to figure out its expectation, of course I'll have this integration over all the possible values that my future lifetime can take multiplied by in the integrand, I'll have this thing again, the value that it takes multiplied with the precise probability for each of these particular values. So this will be my density that I will have in here. So that is what they have done here. So again, because we are looking at Tx, I know that I can start at 0 and the maximum time that I can observe this person is at omega minus x. And then I just expect this person to be dead because omega minus x is the last age that I think people survive up until. After that, everyone must die, at least in the model that we're studying right now. Okay, so now we're trying to rewrite this thing as something else. So let's try to do that. So we have this small f of x, which I can write as the differentiation of the CDF, all right? And I know that I can rewrite my CDF as just TQX, because again, this represents probability that your TX will be less than or equal to T, right? The probability that your the probability that your future lifetime will be less than T, which is precisely also conveyed by TQX here. And I know I can rewrite this TQX as 1 minus TPX. And my d1 by dt is just 0. So what I'm left with is minus of the derivative of TPX with respect to T. And this is what I just substitute instead of this whole term in here. Okay, and now I have T here, and then I have some derivative stuff, and then again T here. But you see, I have integration and differentiation again. So we'll try to use integration by parts and using again just the formula that you guys have in your booklet, you will arrive at this. So I think the only term that they have messed up here is where you differentiate this T guy. So it's just 1. So yeah, and the rest of it is, I guess, pretty much clear because you'll have integration of this guy. So you'll just have TPX and you have T here as it is. And then you again have integration of this guy. So again, this is just TPX. And yeah, minus, you should never forget that minus. So this is what you get at the end. And now if we try to evaluate this first term, what do we have? So we are looking at the varying values of t from 0 to omega minus x. And what we have is t times tpx. So I know for my t taking the 0, it's essentially 0. So the only term that matters is omega minus x times omega minus x px, right? So what do I mean here? What do you think will be the value for this particular guy? So even before you tell me the value, tell me what does this mean in words? Anyone?
Probability that the life age X will survive at least omega minus X years.
Right. So this is given that the life is already aged X, right?
Yes.
All right. So what do you think the value for this thing should be? Do we know something about this person, about this particular value, on this particular term? So what is omega minus x here? Anyone? Okay, let us start from the start. What is omega? Omega is what I have defined can be the maximum age of any person in my model, right? And x is what I know the person has already survived for, right? So when I'm talking about omega minus x, px, what do I mean here?
Remaining lifetime of the person.
Right, so, and what will that be? It is just going to be 0, right? Because I mean, anyways, the person is expected to be dead by the age of omega. So even though I have omega minus x, I know that this person has been alive for x years at least. So if I add that, I get omega. And I expect no one to survive up until omega. So this is going to be 0. Because omega is again, just the maximum. And again, because we are looking at the precise probability, this term becomes 0. And the other term that we have to subtract, which is again 0 times 0 px, that will also be 0. So what you are left with at the end is just this part, which is the second term that you had here. And that is your precise answer for the complete expectation of life. So let me just go back and write this result in our flip chart. Okay. So if I'm looking at complete expectation of life, I denote this thing as E circle X, and this is nothing but expectation of the future lifetime of a person who is already aged at X. And this I know I have just derived. Okay, so one thing, what we derived was this. So we had from 0 to omega minus x. And now these limits can be tricky as well. So does it matter if I observe or if I increase this limit from omega minus x to infinity? No, right? Because for any value which is greater than omega minus x, I know that the value of tpx is just going to be 0 for all that is greater than or equal to omega minus x. So it doesn't matter much. So what I do is, instead of writing it carefully as omega minus x, it doesn't matter because the rest of the terms are just going to be 0 in the integral. So I write this as integration from 0 to infinity tpx dt. And that's it. That is how you will denote your complete expectation of life. And now what you can do is maybe go to the formula booklet that you have and again see the page number 68, let's say any page number. Yeah. So now if you have a look at, let's say, let us just have a look at, the 5th and the 6th row. So when my life is aged 5 and when my life is aged 6, what do you see? Is my value of complete okay, so the very first observation, if you see E circle X, it is decreasing in its value, right? Which is what we would have expected, because as and when the person's age increases and it nears the omega, we expect the future lifetime of this particular person to be lesser. So it starts off with 73 and then it decreases from then. Okay, that is fine. What else do you observe? So let's say if I have to make some connection, again, so let us just say that, what is the expected future lifetime? Okay, so maybe if I put it this way, if I tell you guys that the expected future lifetime for a person aged 9 is 65, I'm ignoring the decimals for now. So let's say if it is 65, Okay, no, I should take into consideration the decimals. So if I'm saying that the person aged 9 has expected future lifetime in complete sense of 65.183 years, then what happens after 1 year? What ideally you should expect is, if let's say previous year my expected future lifetime was 65.183, then it should just decrease by 1, right? Because I have lived for 1 year now, so my expected future lifetime from 1 year later should just be 64.183. But if you see in the table booklet, it is not that, it is a bit higher than that. And why? Because again, the conditional thing comes into picture. So if you observe carefully, this expected future lifetime at age 5 is less than 1 plus the expected future lifetime at age 9. So it's a bit higher. It's only a difference of, 0.12 points, but it is still a bit higher. So there is no one-to-one connection here, because again, the very fact that you have survived for 1 year, it didn't contain, 1 year in your expected future lifetime. So there is some thing going on over there. But I just hope that these observations give you some sort of way to think about this, and the way in which you should not think about these future expected lifetime. Because this is not the future lifetime, this is expected future lifetime. So there is no one-to-one connection. So maybe I should just write it here, that my E0x is not at all equal to 1 plus E0x plus 1. Rather, I can say that my E0x is always going to be less than 1 plus E0x plus 1. So this, I have 1 here and I can change this, but yeah, I guess this is what we have for now. So this is some result that we just observed. Any doubts in what I have just explained? Okay, so now let us try to look at the other way to figure out the future expected lifetime. And this is actually known as Curtate expectation of life. And we denote this guy as K subscript X. So when I'm talking about, the future lifetime of a particular person who is aged X in Curtate sense, what I actually do is, if I have, let's say, some number as 36.45. So right now we saw, right, it was something 64.183 or something as the expected future lifetime. But when I'm talking about Curtate, I do not take into account the fractions, the decimal points. I do not take those into account. I only care about the integer part, and that too, let's say if you have 64.9, it will still round down to 64. So every time you round down to the nearest integer part, and that is why this is known as Curtate future lifetime. So this Tx represents the future lifetime, and if I put 2 square brackets, I am only caring about the integer part of the whole number. So that becomes your Curtate future lifetime random variable. So now we'll try to see what happens in this particular case and what is the probability density for this particular guy. So what I want to care about is the probability that this kx takes some particular value k. So the probability that this person's future lifetime is equal to some value of k. So again, when all will the future lifetime of this particular value be equal to k? So because I'm looking at Curtate, and I know that even if I have my Tx as, let's say, 64.1 or 64.9, both of these, so the value of my Tx being this or this, will give me the same value of Kx, right, as 64. So I know that my probability that Kx takes the value of K is just equal to the probability that this Px takes a value in between k. So I can put a equal to here, but I can never put a equal to in k minus 2, k plus 1 here. Because let's say if this becomes 65, then this is not 64 anymore. But if it is 64, my kx will still be 64. So for k less than or equal to, and for k plus 1, this is just greater than. So I hope this makes sense. And now once we have that, what does this mean? In terms of probabilities, so again, now we care about the integer terms. So I will not try to use the mortality rate mu here, which is the instantaneous. Rather, I can go for Q. So what I'm going to do here, I will say that the person was aged X and it is alive for K years, and now he could die anytime, right? After K years, I don't mind, he could die anytime, but he should be dead by at least X plus K plus 1 year, right? He should not be alive by that time. So this is what you get. And there's actually some another term that we can again use to denote this particular probability. So here if you see, what I'm trying to say is that this person could be dead anytime, right? After K. So after K, there is no foundation about when this particular person would be dead, but only that it should be dead within 1 year. So sometimes what you can use is something like, so QX, and here you will just write a bar and you will write a K here. So what this will represent, so this is actually read as K deferred QX. So K deferred QX, because you have deferred the chance that you will be dead by K years, right? You can be dead only after K years. That is why you have this thing as K deferred QX. So again, this is just something about the curtailed future lifetime random variable. But now if I want to figure out the actual expectation value for this guy, let me just change this color. Let's say orange. No, I think it should be just blue. Okay, yeah. So now the actual expectation of life. So what was this? This was about the future lifetime, not its expectation, right? And what we care about is this expectation of the future lifetime. So this is, so I'm not going to derive this, but again, this is just going to be a discrete version. So only difference here, K starts from 1 and you have this summation. And you have this omega minus X, K, P, X again. So this is the same thing. And again, I mean, it doesn't really matter much if you erase this and if I write it as infinity. Because again, the rest of these guys will just take a value of 0. So this is important. So whenever I'm talking about complete expectation of life, it is something like this and denoted by this. And if I'm talking about curtailed expectation of life, denoted by this and something like this. So these are just some terms that we ought to know. And you can, I mean, there's a whole derivation of this formula in the book, which you can see for your reference, but I'm going to try to cover that. Okay. So now let us try to do one sum from the book here, I would say.
Ma'am, are we expected to know those derivations well?
No. But again, I mean, there's actually nothing going on in the derivation. What they've done is K times KPX times QX plus K. So, I mean, if you read it, you will understand it. And if you still want to, if you still have some doubts, just let me know. I'll explain it. No worries.
Ma'am, where did the K come from? Like summation K into KPX, that part. So where did that K come from?
So where did this, because we're not talking about expectation. So what is expectation? It is X times the probability that you observe.
Yeah.
So this is the value. Because, so okay, this K might be a bit confusing. So this KX we have denoted as small k. That is why you have this small k here. Okay.
Yeah, got it.
So Perfect. So this is something, a very nice relationship that they have defined between the current expectation of life for today and for 1 year later. So we saw that, not there wasn't a very nice relationship with equal to sign, at least for the complete expectation of life. But if we see here, there does exist a very nice relationship. So we'll try to prove this. This, I think, is really nice. So what they are trying to do here is figure out and basically try to prove that this is equal to that. Okay, so now when I'm talking about EX, what do I mean? What is my EX here? Can someone tell me what is my EX in words? This is the current expectation of life, right? And I have just written its formula. So let me just go back, I guess. So what we have seen is this is just summation where k goes from 1 to infinity for kpx. And that is the same thing that I'm going to do now. So I'm just rewriting this summation up until infinity, right? For 1px, 2px, 3px, and so on and so forth. And then what I do is I know using the thing that we studied previously where we took this S and P and this, that is known as the consistency condition, where you can have a look at 2px as separately, where you can just say that you observe this particular person being alive for the next year, and then you start off at x plus 1, and then you again look at it for the next year, so that you are indeed looking at 2px. So again, 2px can be written as px times px plus 1. And if you are talking about 3px, this can also be written in terms of px and then px plus 1. But here you'll have to, because you're looking at 2 years ahead of x plus 1. And if you do that, you can take px as common, and you'll have 1 plus px plus 1, 2px plus 1, and so on and so forth, which is nothing but ex plus 1, if you try to expand it in a similar fashion. And that is how you get this particular relationship, which is very useful. So let's say if you know EX and if you know EX plus 1, then it's very easy for you to derive PX, right? So I hope this is making sense. But again, I mean, what we'll try to do now is again the variances of these particular guys. So these are actually not of much importance, but I just want to cover it because they have also given it in here. So for variance, we will just do t square here and k square here for expectation of the respected random variable square, and then we'll subtract these squares. But yeah, these do not simplify neatly as the expected values do. So we do not have to concern ourselves with these, but we'll try to look at the other kind of models that will fit. And for them, we would be able to figure out the variance, not for these particular stuff that we have just seen. Okay, so now this is also very important relationship between the complete and the current expectation of life. So we know that these both look at the same thing, but one looks at it in continuous way, and this guy is looking at it in a discrete manner. So there is some sort of a relationship that exists, and I think it is easier for us to guess which one of these values will be higher. So the more number of terms you add, the more likely you will observe a particular higher value. So here you know that this complete expectation of life is just a half added to the current expectation of life. And that is one approximation that they have derived here. So let me just write the relationship as well, because that is also very, very important for us. So EX0 is approximately equal to EX plus a half. This is important. So what generally happens is so if we are looking at, the E of X, we assume that deaths do not happen at the actual time they happen. We just assume they are uniformly distributed, or they happen halfway across let's say if we're looking at X and X plus 1, then we just assume that every that we have observed is at X 0.5. So sometimes these assumptions might just make our lives easier. So yeah, this is the relationship. That is actually very, it holds true for most of the applications that we'll see. So I guess that was it. And now it's just time to see some important formula. So in your books, actually, I don't know why they have, okay, yeah, maybe, no, but again, I don't know. So they have actually given a full derivation again of PQX and PPX. So, but I do not want to go through all of that. I think we have learned enough to directly make sense of these integral expressions. So I think this is something that we have always seen, right? So what might help you is to just recall that we have a live state and we have a dead state, and the mortality rate is denoted by mu, and again it depends on the age x here, right? So what I'm just doing is, here I'm trying to figure out if a particular person is aged x today, what is the chance that this particular person will be alive by time x plus t as well? So we have already seen this before, right? This is something like occupancy probability. So this is what the total force of transition out of the alive state, which is mu x plus s. And here you have ds, and this is going from 0 to t. So, or you would have this as x, and this would be p plus x. So it would give you the same answer if there were just a s here and then a ds over there. So I hope this makes sense. And this PQX is again nothing but just accounting for all the times when you might be dead after S. So after X plus, you should be dead by the time of X plus S. But again, so remember, what is my PQX? It does not tell me that my person is aged X today and he'll die at the age of X plus T. It only tells me that when I observe this particular life at X, he is alive. But when I observe this particular life at X plus T, he is dead. So he could be dead anywhere between X and X plus T. And that is why, to take into consideration all the possible values that you can have for this t guy, which again, so now you just replace it with another random variable because you're taking ds, and the maximum it could go is till t. So that is why you start from 0 till t for s. And then you are just saying that this particular person is alive till s and then instantaneously dies. So taking into account all the particular values of s that you can have. So I guess this is a very simple interpretation, and you need not know all the derivation and stuff. And even though if you try to do this derivation, this is fairly simple and similar to what we have done. So it uses some boundary conditions and blah, blah, blah to figure stuff out. But I hope this integral equations make sense to you. Any doubts in this? Anyone? All right, so now let us try to move forward. And this is way much more interesting. Okay, so what do we have here? Wait, what did we just study? Yeah, I guess, let me just save this. All right, okay, so now what we are trying to study here is some particular model. So remember, what we care about is what is the probability that we will observe some people to. So we are looking at the probability that we'll observe some people to survive after a particular age, right? So TPX is what we're looking at, which again I can rewrite as Sx of t. And if I assume that my mortality rate is constant, so now we will try to have a look at what happens if we differ the way I define my mortality rate, and we'll see at different things that we can do and different kind of models that we will see for the survival function. So this is my survival function, and if I assume that my mortality rate is constant, which is for the mu here, So if I'm assuming that this is just a constant, so I only get a mu here. So for 0, it's just going to be 0, and you'll only be left with e raised to minus mu t. So if you have a look at again the probability that you will be dead by x plus t, this kind of reminds you of exponential distributions, PDF. Sorry, the CDF, right? So this is 1 minus e raised to minus lambda t, something similar to, but here instead of lambda, you have a mu. So over there, lambda was the rate at which certain things occur, but now mu is the rate of mortality here. So that is just something that we concern ourselves with in this particular case. So this will be the case when wherein you see that this survival function actually follows exponential model because of the fact that you have this e raised to minus mu t here. Okay, and they have just given an example here. So again, so if you have 10p25, it doesn't matter, right? If you have 10p35 or something else as well, it would still give you the same answer. So for every time if you want to figure out the probability that you will be alive for next 10 years, it is going to give you the same value because your mu is just constant. It does not depend on what age you are starting at. But again, this is not fairly intuitive because we know that age does matter. So there is this another model that you can actually use, which will give you some viable type shape for the survival function here. So again, remember this viable is just some sort of a formation of exponential distribution. So we'll try to see the connection between this and the exponential model. But again, if we just have a look at this f of x for this particular guy, you will see that it corresponds to the CDF of the viable distribution. Okay, but again, before even we do that, let us try to derive this. So what we saw was that TPX is nothing but e raised to minus integration of mu ds. Here I had x plus s and something and so forth. So this I know can be written as sx of t. So if I rewrite this thing as s of t, and if I apply log everywhere, what I get here is a minus integration of mu x plus s ds, right? And let us say if I take this minus here, and if I differentiate this thing with respect to dt, here the minus will go and the integration will go and the ds will go. So what you get is this particular thing here. So your mu x plus t will be equal to minus the differentiation of log of sx t with respect to t. And then you can easily see if you derive this particular thing, assuming that this is the model, survival model that you take into consideration, then if you differentiate this thing with respect to t, what you will have is minus alpha as it is, and beta t raised to beta minus 1. And minus will still be there. So you have that, and I guess if you just try to differentiate, what you will get at the end is something like this, which is what? Just alpha times beta e raised to beta minus 1. Does this make sense to you guys? So again, we should also consider, we have 1 minus here and 1 minus here, so these cancel each other out, and at the end what you have is some positive number. So this is what you get for the mortality rate at x plus t. So in the exponential case, it was just constant. It was just some mu, right? But here now, if you see, it depends on t. So it varies with the age that you are looking at. It does depend on t. And again, depending on what value your beta takes. So let's say if your beta is equal to 1, then this will just be t raised to 0, right? And you will have alpha times beta, which is what? So I've also assumed beta as 1. So this will become 1, and what you'll be left with is just alpha, which is what is the case with the survival model in the exponential case, right? So this is just one constant. And now if you have beta greater than 1, then you see that this is t raised to something positive. So you see that if you increase your t, your value of mortality is going to increase, which is what makes much more sense. But also if you have beta value less than 1, then this would be monotonically decreasing function of t. So the mortality rate would be decreasing as and when you increase the value of t, which could happen, I guess, only in the case of witches, not in the case of humans. At least up until now, we don't know what research people are doing these days to reverse aging and stuff. But yeah, this is what we know. So again, so if you see this kind of a representation for our survival model gives us much more flexibility in terms of the shape and in terms of the rate at which we might figure out the mortality. So I guess this is good. The next thing that we will study is, there were these two people, one is Gompertz and the other one is Meckham. I don't know how to pronounce this people's name, and I certainly haven't looked up. So forgive me if I mispronounce these people's name. But yeah, so what happened with Gompertz was, in the year 1825, he saw some kind of a graph, which they've actually shown here. So what he tried to plot was, he plotted the mortality rate. Again, you see these numbers, it doesn't really, I mean, this caps at 1. So this is actually because we are observing this on a logarithmic scale. So what happened is, he saw a graph like this. So you see there's some bit weird going on here. But if you see, this is, so to his mind, this was fairly linear. And that is why he said that at least for the middle ages and for the older aged people, if I assume my mortality rate to be this thing, it works really well. And it did work well. So it still works well, but only for, middle ages and older ages. And again, we'll see. So this is like a very lazy approximation that you can do. But yeah, he saw some geometric pattern, and that is why he said that we should have x in the power here. So this x here represents the age at which we want this person to be dead. So according to Gompertz, so whenever let's say if I'm said that I have to use Gompertz law, then you have to assume your mortality rate as BC raised to x. Now this B and C are some parameters for which we will figure the value of. So let us say sometimes what you know is mu value for 50 and mu value for 55. So now if you know this guy and if you know this guy, you can easily figure out the value of B and figure out the value of C. And now if you know the value of B and the value of C, you can easily predict what can happen for, what will be the value for mu 65, 75, and so on and so forth. Because you have defined mu of x as BC raised to x. So that is what you have in the case of Gompertz. But again, there is a nice derivation that they have given for the TPX. So this is a bit tricky, I would say, but there's not much tricky thing going on here, only one thing. So in the case of Gompertz, we have to prove that my survival probability is nothing but something like this, where my G is this. I think these are given to you in the table booklets, and you will certainly not be asked to remember these, because even if you know just the fact that in Gompertz I write it as BC raised to x, you could always derive this particular thing. Okay, so now I'm just going to walk you guys through the derivation here. And I think they have done it in a bit complicated way, and we won't do it in that complicated manner. So let us try to do it in our own way. So what do we have? We have TPX, which we know I can rewrite as e raised to minus integration from 0 to t mu x plus s dx ds. And I know how I rewrite my mu x plus s in under Gompertz law. This is just BC raised to x plus s. So once we have done that, we now just have to figure out the value of this guy, right? But even before we do, we just if we can figure out the value of this integral, it's going to be good for us. So we try to figure out the value of this integral here. So what we have is integration from 0 to t. B is just a constant, and again, I'm just going to have c raised to s inside, because that is the only thing that depends on s, that is changing it. So this will be nothing but cxb and c raised to s upon log of c from 0 to t. And if you do this, this is precisely what you will get. So again, because my log of c does not depend on s, we can take it outside as the common, and you'll be left with c raised to s from 0 to t. And if you do that, c raised to t and then minus c raised to 0, which is just 1. So this is what you get for the whole integration part. So now let me just try to erase this part here. All right, so this is what you have, and let me just write that this is nothing but bc raised to x upon log of c and c raised to t minus 1 for the integration part here. Okay, and now what they have just done is defined g in such a manner. So this is not very complicated, I would say. Simply, if you see minus integration from 0 to t, we see the same thing. The our stuff that we had here, we have taken in here, and now what we've done is we have just written this thing as what we just derived here. So we have c raised to x, we have c raised to t minus 1, and what we were left with is b upon log of c. And what they've done is just defined my log of g as something like this. So then that you can easily replace again with minus here with log of g instead of minus b of log of c. So once you just do that, what you get at the end is something like this. So this is g raised to cx times ct minus 1. Again, why? So remember we had log of g here, and now if I do e raised to everything, maybe I can just do it. If I do e raised to this thing and e raised to this thing, what will this become? This will become e raised to log of g times e raised to this stuff, and this will become just a g here, right? So this is what you get for things at the very end, and this is how you will have derived your value of TPX for the case of Gompertz, when you assume that your mortality rate is just BC raised to X. Okay, now this Neckham guy, very interestingly, what he did was he just added a constant to what Gompertz suggested. Just add some A so that it also takes into account the case where your A value is just 0, right? Which is what you will have in the Gompertz case. So now this is something slicky, and if you just try to derive the survival function for this guy, we will. So what is the sum that they've given here? Yeah, so these are the kind of sums that you will get, but these are very unlikely because these are very easy. So you'll have the value of mu 70 and mu 90 and just figure out the probability that a life age at 60 will survive for 20 years. So once you figure out the value of B and the value of C, you know the value of mu X. And now if you know the value of mu X and the link between these TPX and mu X, which is what we have just derived, you can easily figure out any probability for any particular person being alive or dead after so and so many years. Okay, so the similar thing we will do for the Meckham's law, and again, I'm not okay, yeah, even they haven't derived it. So, okay, there won't be much change in the derivation again. Because if you see what, just give me a minute, guys. Okay, sorry about that. Yeah, so what we have here is just a added, right, to the BC guy. So what you will have here is in the numerator here, you will have a plus BC x plus x. And you can just take this e raised to minus this integration from 0 to t a ds as some another term, because we have e raised to a plus b. It can be written as e raised to a times e raised to b. So you see that there will be only a bit of change here. So you define this s raised to t as e raised to minus a. So I guess there will be some minus that you will see somewhere down the line in the derivation, but yeah, it's going to be fairly similar. So this is the value of TPX that you get in the Mayhem's law, where you have the mortality rate as some constant plus BC raised to the age at which you expect the person to be dead at. Okay, and now this is the last thing that we are studying, and I'm leaving you guys in 3 minutes. So this is what they call as Gompertz Mayhem family, where ignore this first part for now and just have a look at here. So this G is for Gompert and this M is for Mayhem, and these are the degrees of polynomial that you're looking at for each of these particular people. So again, this polynomial 1 is a function of t, and then you have e raised to some polynomial a function of t. So why do we have these two polynomials? One will account for the constant and the other one will be accounting for the exponential and the geometric progression that we see in the ages as and when we increase the age, and as in when we looked at the mortality rates. So this here, we expect it to be a linear function of x. So again, what is my t here? What does my t denote? Anyone? Can you tell me what does my t denote here? T is the time for which? Anyone? Do you guys know what is my t here? So generally what I look at is TPX. It's the extra time that I want this particular person to be alive for, right? So what you're just gonna do is, so this is, actually maybe I should write this. So what we saw was, let's say BC raised to, oops, let's say BC raised to X is what you have in terms of Gompertz, right? So you can just put a E and a log here. Okay, let me just write this all again. So if you have e raised to log of b c raised to x in case of Gompertz, you can just rewrite this thing as what? E raised to log of b plus x times log of c, right? So now this thing that you have in the numerator is some polynomial that we are talking about here. So this is the family that they're defining. But again here, instead of these just 1 and 2 terms, what we are having is, we are looking at the whole family, and that is why we have this alpha 1, alpha 2, these parameters, and this is what we will try to estimate. But again, you will have e raised to certain another thing here. So this e raised to log of b will just boil down to b, which is the constant that you observe. So these are all constants, and then you have e raised to some terms, where if you see this a, these alphas depend on r, right? So here these are just alpha till r, and then here you have alpha r plus 1, r plus 2, and so on up until r plus s. So these are just accounting for the r plus s constants that you will observe in this whole polynomial. And this accounts for the t's, and again this accounts for the e raised to guys. So I hope. So again here, I mean, this will again just be used to try to figure out the force of mortality. But again, what these denotes here, so this r here, what you have is the degree of this polynomial. So the highest degree that this polynomial has will be the degree that you have here, and here you have s. So this is t raised to s minus 1 over there. And in short, you can just write this as a polynomial 1, and this thing will be the polynomial 2. So again, these are polynomials of t, because t raised to 0, t raised to 1, t raised to 2, and so on till t raised to s minus 1. And here you have t raised to till t minus till r minus 1. So yeah, I guess that is why you have this polynomial 1 and polynomial 2 here. So this is a function of r and this is a function of s here. So yeah, these are just again, so I think if you I think you will be learning about this in r much more depth, and you'll see the graphs, and that is when you will directly derive the connection between what we have studied and how the things look like. So you will see how it behaves exponentially if you take the mortality rate as constant, and you'll see how it has a shape like Weibull. So even in Weibul's case, we know that it depends on the parameters, right? The values that this particular parameters will take and the shape the graph will look like. So I guess this was it about the survival models. But again, we didn't really learn anything new in terms of concepts here. But what we did was just build up our toolbox to study the next chapters. So I guess this is all from my side for today. And I would encourage you all to try the end of the chapter questions for this chapter number 6. And I'll see you guys tomorrow. So we'll try to do some questions from chapter number 6 tomorrow, and maybe some questions from chapter number 5 as well tomorrow. So tomorrow I won't be teaching anything new. We'll just solve and try to see what all we have studied and try to use that in solving the sums and basically just build up our understanding at a much deeper level. Okay, so I guess that's all from my side for today. I'll see you guys tomorrow.
Thank you, ma'am.